University in Electrical Engineering. He went to MIT to do his PhD. He got a PhD in Electrical Engineering and Computer Science, working with Jim Fujimoto. And so Vivek did some really nice pioneering work on 480 OCT for really fast retinal imaging with Jim. And then from there, he went to Martino Center at Massachusetts General Hospital or med school. There he worked with David Boaz, with Iodophor, with the whole slew of people at Martino Center, where he worked on use of OCT and also two photon microscopies and diffuse correlation spectroscopy. So all our favorite optical technologies. We're looking at pseudovascular architecture and function as well. And then from there, he was an instructor also at MGH, and then he went to CS 2012, where he did the medical engineering department there. And then he became faculty, also joined or courtesy appointment with ophthalmology. Are you split or are you?
Courtesy.
Courtesy appointment with ophthalmology. In 2016, he got tenured in the department, so he's associate professor now. And in 2018, found that he became a cancer fellow. He's one of, I believe, 12 in that class. And it's a high distinction at any of the UCs for basically recognition of outstanding research. And so he's been working on both 50-50 on neuroscience as well as ophthalmology. And so today he'll be talking more on the neural work and human is using interferometric techniques to improve diffuse optical flow techniques for looking at for application to humans. So with that, please join me in welcoming Vivek.
Okay, thank you. Thank you, Bernard. That was a great biography. I feel very old after hearing such a long biography. And by the way, you have a great memory. I'm amazed you remember all the dates without needing a prompting. So I'd like to talk today about our work in developing better ways to use optical techniques to monitor blood flow in the human brain. As Bill mentioned, I am from UC Davis. I will be moving to NYU soon, so these cows that I see outside my office can be replaced by traffic cars, taxi cabs, pedestrians, etc. My research program is divided into kind of three different areas. We do a lot of work in OCT. That's where my original training was. So area one is deep brain microscopy. We look very deep using longer wavelengths into the deep cortical and subcortical regions. It's an in vivo image of the mouse brain. We're looking at a lot of the same changes in Alzheimer's disease and vascular dementia that some of the groups here are studying as well. We also have a research effort in eye imaging, and in particular, we're looking at changing the wavelengths of the standard of care. The standard of care being, or standard of clinical practice is near-infrared OCT. We're looking at using shorter wavelengths, visible wavelengths of light to image the eye, with the idea being that we can use the same wavelengths of light that the eye uses to see the world to take images. And so we can measure now molecules related to retinal function and also just get really nice high resolution pretty pictures because of the shorter wavelength. And the last area which I'll be talking about today is brain spectroscopy. This is an area that I know all of you are familiar with, particularly because of Bruce Tromberg, who is unfortunately left, but I understand still leaves a big influence on the center. So just to remind everyone, in optical techniques, we kind of divide them into two different classes. The kind of high resolution pretty pictures that we get, this example of a neuron with a calcium dye. In high resolution microscopy, we're usually looking at the light that travels through tissue to the focus and then back to the detector. And usually this light should travel to the focus without scattering. So if we imagine we have a thick tissue, we have an incident pulse of light going through. Some of the light will travel through the tissue without scattering. We call this the ballistic component. And there's a number of techniques, two-photon microscopy, confocal microscopy, OCT, that all rely on ballistic light for imaging. On the other end of the spectrum, if we imagine now we have light that scatters a few times, we have light that scatters many, many times, which we call the diffuse component. This diffuse component is highly scattered, so it doesn't carry with it high spatial resolution information, but it's deeply penetrating. And so the area of diffuse optics aims to assess this diffuse light. This is now, you can imagine, as a temporal response of the medium would carry information about the observers and scatters in the medium. Diffuse optical spectroscopy or diffuse optics attempts to analyze this component to form macroscopic images. Okay, and so the reason I'm presenting this way is typically these areas of research are well separated and distinct. We've recently done some work that's actually taking ideas from the microscopic world, from OCT, and applying them to making better measurements of diffuse optics. Okay, so first, the idea of OCT is that we have, we want to make high-resolution cross-sectional images of tissue. I know you have a great OCT group, Dr. Zhangping Chen. I'm sure some of you might be from his lab. I look forward to meeting you later. We usually say this is the optical analog of ultrasound. We form images, cross-sectional images of tissue from backscattered or back-reflected light. And what OCT aims to do is measure the echo time delay of light to form a cross-sectional image. Now, because the speed of light is much faster than the speed of sound, we can't actually detect those echoes directly, and so we use techniques called low coherence interferometry. Now, there are two principles of low coherence interferometry that everyone from the OCT world knows, but I'd like to reiterate here. The first principle, if we imagine an interferometer here, we have a reference and a sample arm. They're divided into two arms. The backscattered light from the sample interferes with the reference arm on a detector. Now, the first principle of OCT is that we measure the cross term between the reference and the sample fields. Okay, and so this means if we have a very large reference field, we actually can boost up the weak light signal from the sample. And so this means that in OCT we can use now very inexpensive detectors, and this is responsible for some of the success that OCT has had over the years. The second principle in OCT is now, if in the previous slide I had a coherent light source which was at a single wavelength, as I change the position or the distance between the reference and sample arm, I'll see a clean oscillation of the interference pattern as light is interfering constructively and destructively. This is actually just the cross term that I'm showing here. Now, if I use a light source that has many wavelengths, instead of a single wavelength, I use a low coherence source, a temporarily incoherent source. Those many wavelengths will all spectrally interfere such that when I look at the interference pattern, again, I only get interference when the reference and sample paths are matched to within the coherence length. Okay, and so this is really the origin of the axial resolution, the cross-sectional resolution of OCT, is that this idea of low coherence interferometry, that using many wavelengths can provide time resolution in a tissue sample. And so in OCT, the axial and transverse resolutions are decoupled. One other very interesting aspect of OCT, which is responsible for some of its success, is that all of the components we use here are fiber optics. And a lot of these components have economies of scale associated with them from the telecom industry that were existing already. And so the reason why, one of the reasons why this technique has grown is because of it was able to leverage an economy of scale that makes these components high performance and relatively inexpensive. And so as everybody who's been to an ophthalmologist will know, OCT is widely used in retinal imaging. Here's an example of a visible light OCT image from our lab that was taken by scanning the light beam transversely on the retina. So as I mentioned, we're looking at applying these techniques now from microscopy and OCT, which tries to isolate the ballistic light, to a macro imaging that uses diffuse light. And so it's worthwhile to reiterate some of the advantages and disadvantages of this approach. So one advantage of this approach, which comes from the idea that I have a very strong reference light beam, is that we can actually achieve a shot noise limit equivalent to that achieved by photon counting, but without actually needing to use the expensive hardware associated with photon counting. The second is that narrow time gates, achieving at very high time resolutions to detect those echoes of light, can be achieved with very broadband light sources. And so some disadvantages of this approach, which have to be concerned about, is one is phase stability. It turns out this concern is largely mitigated if you image fast enough. And then the other concern or consideration is that there's a high cost per mode for detection. However, OCT is widely used. And in fact, the market for OCT, I think, exceeds $1 billion and is expected to grow even more in the coming years, mainly driven by the ophthalmology and cardiology applications, which I discussed previously. And so we don't want to do OCT, right? We want to apply these techniques to image the whole human brain. And so I just want to give a flavor for some of the techniques that are out there. If we're thinking about brain signals, probably the most direct and relevant brain signal is that of neuronal activity. It's an example of electroencephalography, which are measuring essentially field potentials originating from groups of neurons, mainly in the cortex. This is a direct measure of neuronal activity, but it's quite low spatial resolution and relatively difficult to localize. Now here's another method for neuroimaging. This is functional MRI of the human brain. As it turns out, this is the two different stimuli showing activity in the visual cortex. And the functional MRI signal we'd like to think of this as being due to brain activity, and in fact, it appears to localize very well with brain activity. But if you go through and look at what's creating this signal, this is for blood oxygen level dependent functional MRI, it's actually coming from blood flow. And so from the area of functional MRI, we know we can get very beautiful maps of brain activation. It tells us that actually blood flow is a very useful brain signal to measure. And so in the terms of optics, what do we have? So here's the kind of standard near-infrared spectroscopy. You have your oxy and deoxyhemoglobin, lipid absorption, water absorption, and we use near-infrared light to measure absorption of different chromophores. I'm not going to go into all the details of how this works, but I want to point out some specific issues that are very particular to the human brain. And so for near-infrared spectroscopy, we have an emitter and a detector, which are separated by some distance. You can see the light that travels between the emitter and detector has to travel through the superficial tissues, the skull, dura, arachnoid matter, cerebrospinal fluid to get to the brain. And so these superficial tissues also have hemoglobin. They're also changing with the systemic physiology, and that may not relate in any way to brain activity, which we'd like to measure. And so the main issue with these kind of nearest techniques for measuring brain activity is really the issue of scalp contamination. By scalp, I really mean all the superficial tissues I just mentioned that are not part of the brain. And a typical figure for a near-infrared spectroscopy is really 30%. So at best, you can get 30% brain to scalp sensitivity. Okay, so when I saw this figure, I was pretty amazed that people are showing images of brain activation with NIRS, and they're only able to get 30% brain to scalp sensitivity. And so they usually do this by techniques such as superficial regression, a lot of averaging, maybe some data selection. And so we kind of asked the question, can we develop methods that improve on this number? Okay, and why do we want to do this? Well, if you're monitoring a patient in the neurointensive care unit and you see a change, you'd want to know that that change is specific to the brain and not something that's happening with systemic physiology or due to the scalp. If you're using this kind of a device for a brain-computer interface and you want to think something and have a mouse move in a brain-computer interface, you want to know that those changes are specific to the brain, and you want to be able to do those kinds of experiments on a single trial basis without needing to average many, many trials. Okay, so in terms of optical signals, what optical signals can be measured? There's a lot of different kind of proposals for different optical signatures that relate to different aspects of brain physiology. At the top, we have hemoglobin absorption, but there's also fast scattering changes. There's changes related to transport and intracellular motility. And lastly, changes related to red blood cell flow dynamics. And today, I'm going to discuss really hemodynamic signals. So by hemodynamics, I mean either absorption or red blood cell flow dynamics, which I'll discuss in a few slides. So before we do this, I just want to quickly go over the various forms of NIRS. So the first form of NIRS which is simplest, is you have a source and a detector. You measure the light intensity attenuation between the source and detector, and you see how those that intensity fluctuates over time. And so this is a fairly simple method. We can see here we have a path, again, traversing the superficial tissues, getting to the brain, and then going back to the detector. And so the main issue with these techniques, as many of you know, is that the path length of light travels is unknown. And so this is something else that's going to come up in a few slides. I want to point out that this path length is related to the time of flight, which is very much related to the depth that we think about in OCT. And I'll make that analogy more explicit later on. Okay, the effective path lengths, of course, is not simply the depth in tissue. Of course, when you have highly scattered light, the light takes a tortuous path to get from the source to the detector. And so we can imagine stretching out that ball of string according to the slide from Steve Jacques. And the path length is actually the length of the ball of string. The time of flight is the time it takes from light to travel from the top of the ball of string to the bottom. Okay, and so there are other methods of NIRS that address some of these issues, frequency domain and time domain NIRS. I know you have purchased some time domain NIRS systems from Hamamatsu, and look forward to hearing about how those work. Also, I would be remiss if I don't mention the spatial frequency domain, which is not on this slide, but because we're focusing on human brain activity in this talk, I didn't put it up here, but of course, spatial frequency domain is another more quantitative way of assessing the light path length in tissue. Okay, so here is the equation for metabolism, relating metabolism, hemoglobin, and cerebral blood flow. And so if you think about what hemoglobin signals actually tell you, assuming you could localize the compartment and can measure a perfect oxygen extraction, hemoglobin is still relatively ambiguous. And I think the reason why is if you imagine inverting this equation and moving cerebral blood flow to the other side, I could explain a change in oxygen extraction by a change in metabolism or a change in blood flow. And so oxygen extraction by itself can be very useful, but I would argue it has limited utility in many settings. And so I'm, of course, not the first one to argue this. Many others have argued that blood flow can actually be more informative than hemoglobin alone. Of course, if you have them both, it's even more informative. But if you had the choice of one, I would argue that cerebral blood flow provides a more unambiguous measurement of how much blood supply is going to the brain. And there are a number of applications here where cerebral blood flow is very useful. Okay, so how do you measure cerebral blood flow? This is a technique called diffuse correlation spectroscopy or diffusing wave spectroscopy. And the basic idea is the physical principle is the light source is now coherent. It's a single wavelength. And I shine a light source into the tissue. I observe a speckle pattern coming out. That speckle pattern fluctuates according to the blood flow dynamics in tissue. Every scattering event from a red blood cell will impart some phase change to the light that contributes to light fluctuations. So if I have more red blood cells in the tissue, or if those red blood cells are moving faster, I'll observe a higher rate of fluctuations at the detector. And so diffuse correlation spectroscopy typically measures the light intensity fluctuations. In the case of slow flow, the intensity fluctuates slowly. Fast flow, it fluctuates more rapidly. And from the intensity autocorrelation function, I can distinguish between slow and fast flow, and in fact quantify a blood flow index, which is related to the blood flow in tissue. And so there are a number of techniques that are related to this. Of course, all the great laser speckle work that Bernard is doing and is essentially the same physical principle as diffuse correlation spectroscopy. Okay. Now, in terms of the brain signal, how does cerebral blood flow perform? So here we've compared, using a two-layer model, this brain to scalp sensitivity for absorption measurements versus a kind of a blood flow measurement, okay? And the key point to remember here is that there's 6 to 10 times higher cerebral blood flow relative to superficial flow, okay, in the scalp and the skull. And so this means that the dynamics, the blood flow dynamics are intrinsically more sensitive to the brain when I make these measurements through the scalp. And so here we've plotted in red is the blood flow index at 2 different wavelengths, and in black is the conventional absorption signals at 850 nanometers. We can see that the blood flow index achieves a much higher brain to scalp sensitivity, even at a source detector separation of 3 centimeters, we're at essentially 100%, which meaning we're getting equal sensitivity to the brain and scalp. And we can increase this further by increasing the source detector separation further. Okay, and so the problem is, as I'll describe on the next slide, is that VCS, because it's using photon counting, they can only measure essentially where the black arrow is, although they like to measure at much higher source detector separations. And so the basic reason why this is, I'll go through this relatively quickly, is that to measure a single speckle, you need to use a small core single mode fiber. Single mode fibers don't carry a lot of, or can't detect a lot of light from a diffuse measurement. And so to really detect more light at larger source detector separations, you'd like to use few mode or multi-mode fibers. The problem is for these multi-mode fibers, you can see the speckle fluctuations are now washed out because you're adding many modes, each with independent intensity changes together. And so really the only choice we're left with is use many single mode fibers together. Now what's the problem with this? Well, each single mode fiber has to go to a photon counting detector or photon counting channel, and these detectors can be very expensive. Now there are cheaper sources or cheaper solutions which we can discuss offline, but generally photon counting is very expensive and difficult to scale. And so how do we solve this problem? So this is where all the ideas are coming together. So we decided, well, we'll take our OCT idea where we have a strong reference arm and we'll apply it now to this diffuse optics geometry. Okay, so we add a reference arm to the standard years measurement. If we have a reference arm, then the brain is now the sample arm. And I'm going to argue that this is now enabling a new class of non-invasive in vivo measurements of the human brain that are both more informative and less expensive than the conventional methods. And so once again, we have this cross term, the field between the reference and the sample arm. And this enables, as I'll show in the next few slides, a massively parallel detection, which means we can now scale these measurements to have larger throughput and better brain sensitivity. And at the very end, I'll talk about how we're adding the time of flight axis to get more information from the sample and enable more quantitative measurements of the brain. Okay, first idea is called interferometric diffusing wave spectroscopy or diffuse correlation spectroscopy. And this is using the idea of massively parallel detection of weak light signals. Okay, and so the basic idea here is I saw some of you nodding as I was saying you can't do DCS with a multimode fiber. So this is the reason why. If you add the intensities of many, many modes, each fluctuating independently, these intensities are going to cancel out and you're left with no change. Now, if instead we had the fields of many modes, and I should comment that in the interferometric measurement, essentially what we're doing is adding fields. We can see that this is quite different. So we're still able to observe an autocorrelation function from the fields, and that autocorrelation function still has a decay rate that we can still compute and determine blood flow dynamics. Okay, so our idea is we take this interference pattern and we image it or project it, if you like, onto now a CMOS camera. Okay, and so this was the first system we came up with. We have a line scan CMOS camera. The cameras operate extremely, extremely fast because the decorrelation time of the brain blood flow dynamics are on the order of 10 microseconds. So our line scan camera is operating at 300 kilohertz, and it's measuring the rapid speckle pattern, rapidly changing, calculating the autocorrelation function, enabling us to measure cerebral blood flow. Here's an example on a subject in our lab. This is Renjun Zhou, the inventor or the co-inventor of this technique, who's built this system. So the system is behind him. On the screen, you can see the real-time blood flow fluctuations. As I've shown a few slides, those look noisy, but that is actually not noise. That's real pulsatility of brain blood flow. Okay. The last point, which may not strike everyone, but those who do DCS will appreciate this, is that the lights are on in the lab. Okay, so we're not doing photon counting. We don't care about stray light. And we've tested this up to very high ambient light levels that are typical of a hospital environment, and we're still able to make these kinds of measurements. Okay, that was the first paper, first set of experiments. The second set of experiments, he improved the system, changed some optics around. I'm happy to discuss what we changed. But the key point is he went from measuring 16 speckles to 85 speckles. Okay, and the previous set of measurements I showed was at 2.5 centimeter source detector separation, which is good, but not great. We'd still like to go higher. With the new system, he's now able to get pulsatile blood flow up to 3.5 centimeter source detector separation, and he's able to get reasonable blood flow measurements up to 4 centimeter source detector separation. So I mentioned that with the photon counting measurements, they're typically limited to 2.5 to 3 centimeters. Okay. Showing here just some basically showing experimentally what we know to be true, that if you increase the source detector separation looking at the black squares, we can see that the blood flow index, that measure of the autocorrelation decay relating to blood flow, is increased with source detector separation. That makes sense because as you increase the source detector separation, you have more sensitivity to high brain blood flow and less sensitivity to the slow superficial blood flow, and you'd expect the blood flow index to increase in this manner. Now, how do we validate that we're actually getting brain blood flow? So we did some measurements of hypercapnia, which is a standard measure of cerebrovascular reactivity. We created a breathing circuit, measured end-tidal CO2 during up to 5% carbon dioxide inhalation. And the real gold standard here is that techniques such as MR and PET typically report about 4 to 6% increase in blood flow with every 1 millimeter of mercury of end-tidal CO2. Okay, so for us, that was kind of the bar, is can we explain or demonstrate reactivity, increase in blood flow consistent with what is known from the literature. And so here's examples of some experiments where we did hypercapnic trials. These are 2 trials of hypercapnia. This is end-tidal CO2. We can see, this is CO2 waveform. The blood flow index is shown down here. We have 1 trial here, 1 trial here. Again, this is not noise, this is real pulsatility. Okay, so the pulsatility itself is quite interesting, and we can have discussions about why it's interesting later, but for now, we're only interested in the increase in blood flow. So we averaged out the data with a low-pass filter. We have, again, end-tidal CO2 in green, and now the blood flow index increase in black. Again, this is a typical response. Now, a blood flow index increase, if now we average over, let's go here, if we average over many subjects, looks something like this. Excuse me. What's going on? I think I have a backlog of clicks. Okay, while I'm waiting for my computer to respond, there's basically two issues. Oh, is it done? Yeah, I think we're good. Nope. Okay, so there's two issues you need to think about when you're being quantitative. One is that during hypercapnia, the blood vessels dilate, bringing in fresh oxygen. So oxygenation is going to change, the blood volume is going to change, and so absorption is going to change too. And so I need to take that absorption change into account when I'm recovering my blood flow index. Okay, that's number one. The second is essentially what I described before, that I have this superficial layer of tissue. That superficial layer of tissue has a lower blood flow, but it's still going to affect my deep measurements. And so the way I'm going to account for that superficial layer is to do a two-layer model that I will use to recover more accurate blood flow measurements deep in tissue or in the brain. Okay, so keeping those two things in mind, let's see if I can. There we go. Okay, let's start right here. So keeping those two things in mind, I'm going to take you through a series of steps. And that series of steps will enable us to get quantitative measurements of the change, okay? So here's the hypercapnia trials I showed you before. This is actually the exact same graph that I showed before, another one on the right. If I pull all data across many, many subjects and many trials of hypercapnia, I get a curve that looks something like this, that change in blood flow index versus change in end-tidal CO2. And again, the gold standard, or the bar that I'm trying to reach, is 4 to 6%. Okay, so this data was analyzed with a single layer model, which means I don't account for the scalp blood flow, and I also did not account for the absorption change during hypercapnia. And so this data gives me, well, number one, you can see I do see a clear linear trend with end-tidal CO2, which is great. I'm seeing some kind of a change in the brain that appears to correlate in some way with carbon dioxide levels. But if I look at the absolute slope, I'm only getting about 1.2%, okay, which is still far away from what I would expect. Okay, so now moving a little bit further along and improving the model, instead of looking at using a single layer model to fit the autocorrelation decay, we actually just look at the derivative of the autocorrelation close to zero time lag. And as others have shown, this gives us a little bit more sensitivity to the brain. And so from this data, we're able to see a slightly higher slope. This is now 2.4%, change in blood flow per millimeter of mercury of untidal CO2. Now, if I continue with the single layer model and account for a change in absorption, I see a slight increase in the brain blood flow index. And again, I went from 2.44% to 2.48%, still relatively far away from where I'd expect to be. That's because we're correcting for absorption. And when we correct for absorption, our measurement of absorption is noisy. So we're adding noise to the data in a sense. Yeah. Yeah, we're adding noise to the data in the hopes of getting a more accurate measurement of the brain. So in a sense, we're kind of trying to improve accuracy, but the precision goes down because we're trying to correct for an absorption change. Our estimate of that absorption change is noisy. Okay, next step is now using a double layer model, also looking at the derivative. And so the two-layer model, as I mentioned before, accurately accounts for the differences in brain and scalp. And so we'd expect that that two-layer model would give us a higher brain blood flow index change. And in fact, it does. We went from 2.48% to 2.75% per millimeter of mercury. And then lastly, if we now use that double layer model, but now we account for the change in absorption in our model, we're able to get a number of 3% per millimeter of mercury, which is getting closer to the 4 to 6%, which we'd expect from the gold standard measurements. Okay, so that was a very, at least for me, like a very convincing demonstration that we're able to measure some kind of a meaningful graded blood flow change in the human brain. The next application, which we're very interested in, is measuring functional activity. So here we did a mental arithmetic task. We asked subjects to subtract a 2-digit number from a 3-digit number. The protocol is shown up there. Here's the results. So we can see, again, the black shows the blood flow index, which is relatively pulsatile. Because we're just interested in measures of activity, we can look at low-pass filter version that's shown here in, I think, red. Okay, and the stimulation refers to the mental arithmetic task. And then we also notice that the heart rate tends to increase during the task, so we're showing the heart rate here as well. Subjects might get a little bit stressed out by the having to do math under stressful conditions. So here's the block average results. This is now over 3 subjects and over 20 trials. We consistently see that the flow measurements, so remember flow we argued was more intrinsically sensitive to the brain because the brain just has a really high blood flow. We find that the flow measurements are actually give us a higher contrast to noise ratio for this task than the absorption measurements. Okay, so this is showing that even for a functional measurement, that blood flow may be preferable to the standard continuous wave nearest measurement of brain activity. Okay, and this makes sense because blood flow is what's used in functional MRI. Okay, not last, but last on this section, I wanted to talk a little bit about our new direction. So I mentioned we're using a CMOS camera for doing these measurements. And there's plenty of CMOS cameras in this room. I would wager more CMOS cameras than people in this room. And so what we've done now, hopefully, is we've tied these kind of flowmetry, diffuse optical flowmetry measurements to an existing economy of scale, just like OCT is tied to existing economy of scales. And so we're hoping that this will enable a lower cost, more grain coverage, and more robust detectors. Other applications, autonomous driving, cell phones, computer mice, so CMOS cameras are really widespread and the cost is projected to go down in the future. I won't talk too much about this, but with a low-cost technology, you could imagine making a consumer device now at a very low cost, or you could imagine making a high-end medical device with much higher performance at the same cost as with the photon counting technology. And the last question we asked was, we had this high-speed, expensive sensor for doing these measurements. can we actually use a cell phone camera and use our interferometric DWS to take measurements of brain blood flow with a simple two-dimensional camera? And the answer is, well, kind of, not quite yet, but we do have some preliminary results. These results are taken at now 1 centimeter source detector separation. If you recall the previous slides, that at 1 centimeter, we're not getting a lot of brain sensitivity, but we're still able to see the pulsatile blood flow. This is the kind of like a contrast level, so it has to be flipped if you want to get blood flow index. But we're working on it. So hopefully in the next few years, we'll be able to develop even lower cost alternatives to the methods I just presented for making even more high throughput measurements of brain blood flow. Okay, so sorry for the little hiccup there. So I'd like to go through the next part of my talk very quickly. And this is really asking the question. So we have this, we know that some of the ideas that we took from OCT can apply to diffuse optics. We've shown how this idea of boosting the weak sample field with a strong reference field enables us to make measurements with a lower cost detector. Can we add now time of flight resolution? Okay. And here again, I just wanted to point out this general theme that I've tried to convey here is that the dynamic measurements, the measurements related to blood flow, are intrinsically more sensitive to the brain. And so before I showed as a function of source detector separation, as you increase the source detector separation, the blood flow index is always more sensitive. Now here I'm showing as a function of time of flight. So at a given time of flight, if you imagine doing like a time domain years measurement and comparing it to a time resolved flow measurement, you can see that the time resolved flow measurement is at least 3 times more sensitive to the brain than the time domain years measurement. And so how do we get this time of flight resolution? Well, our idea is essentially the same as the idea for time of flight resolution in OCT. So before I showed you that we use a single wavelength coherent laser. Now we use many wavelengths in the laser, and we tune our laser as a function of wavelength over a very, very tiny bandwidth. We again have our interferometer, which was what we described previously. And so as I tune this laser in wavelength or an optical frequency, the short paths through the scalp are going to give me an interference pattern, okay, that has a relatively slow rate of fluctuations. If I take a Fourier transform, I can reconstruct the time of flight. Now, if I consider a slightly deeper patch shown in green that's just beginning to sample the brain, I have a higher rate of fluctuations in the interference pattern, and that, again, by the Fourier transform, is going to show up in the time of flight measurement. And then a deep path that now samples the brain has a very high rate of intensity fluctuations in an interference pattern, and I can reconstruct that by Fourier transform. And so I can make a temporal point spread function very similar to how one makes a temporal point spread function in time domain years. That is, for all intents and purposes, equivalent to a time resolved measurement. Except we also are able to measure blood flow. So in addition to this time of flight axis, which I'm showing here in red, at each time of flight, we can also measure the dynamics. So we can measure an autocorrelation function at each time of flight, which means we can get time of flight resolved dynamics. Okay, so that dimension is like diffuse correlation spectroscopy. And I should mention there are other techniques that try to do this coming from MGH, which we can discuss offline. Here's an example of our system. So this is a non-contact system. The subject wears glasses because I'm terrified about light safety. And we measure a location on the forehead. Now, if we think about comparing the penetration and spatial resolution in years versus OCT, essentially what we're doing here is OCT, if you were to do an OCT of the human brain through the skull, you wouldn't get very far. So I think you'd measure mostly scalp. However, because of the way we're doing the detection, we detect the diffuse light, we actually get a much deeper penetration than we would get using OCT alone. And so OCT gives us high resolution images, NIRS gives us these temporal point spread functions, which we can use to extract information about the tissue. Okay, so NIRS operates in a very different regime. Here's a similar thing shown again. For NIRS, you need 1 nanosecond of time of flight. For OCT, you need only about 10 picoseconds. Okay, so we're in a very different operating regime than in OCT. And I just wanted to mention here, there's some work from the Fujimoto group at MIT that has actually used a swept source OCT to do very long depth range imaging. There's some differences between that technique and this technique, in particular the wavelength and then the way that the data is analyzed to give us multiply scattered light in tissue. Okay, so now to the results. So we found that when we're taking these now time of flight resolved measurements, we can calculate at each time of flight, we can calculate the autocorrelation function, which tells us about light dynamics. And so here's a plot of time of flight on the x-axis and autocorrelation decay rate on the y-axis, and we can see that the dynamics increases linearly approximately with time of flight. And this is something we found to be characteristic of homogeneous media. This is intralipid, which has diffusing scatters, so we don't expect any changes in the dynamics with depth. Here's an example of the mouse brain, very similar. The decay rates are different. The dynamics in the mouse brain are much greater, but we can still see kind of a linear increase in the autocorrelation decay with time of flight. So we look at now the human forehead. Again, the subject does wear glasses because we are concerned about light safety. We look at the human forehead, take a measurement with a source and detector at 0 source detector separation. We can now see this very interesting kind of biphasic response with a turning point around 600 picoseconds. And so remember that a homogeneous medium kind of just had a linear increase. And so what could possibly be causing around 600 picoseconds, we all of a sudden see the rate of change or the slope change dramatically. We believe this is due to sensitivity to brain. So if you recall back before, we talked about how the scalp blood flow is much lower than the brain. We believe that initially at lower time of flights, we're looking at mainly scalp and superficial tissues. And as we go deeper, we can see immediately and very sharply the differences in dynamics due to the brain. Okay, so let's skip across the end of this. I wanted to show a few slides about imaging. So the cool thing about this technique in a non-contact implementation is that we can then take use scanning techniques that we've learned from OCT to make images using this near-infrared spectroscopy technique. And so we asked the question, can we actually make an image of forehead dynamics with this interferometric NIRS? So here's kind of the setup that we had here. We use a polarization beam splitter to couple the source and detector, and we use a galvanometer to scan the light beam on the forehead. And again, the subject does wear eye protection. And so here's the results that we got. This is now a movie in time of flight. I don't know, can I play it? Okay, so this is basically the time domain NIRS, kind of a measurement of the human forehead. As you can see, the measurement isn't going very deep, so we are at around 300 picoseconds, which is still relatively more sensitive to the scalp. Okay, this one is a little bit more informative. So this is now the autocorrelation decay rate as a function of time of flight. Okay, we can see that there's little kind of hot spots that pop up. These are areas that might have more scalp dynamics. And so those are areas that we might want to avoid if we want to get more brain sensitivity. Maybe we want to put our source and detector away from those regions. Okay, and here's a map of the blood flow index now in the scalp, measured using this technique where we can see we have some hotspots with relatively higher scalp blood flow. Okay, so in conclusion, the interferometric method, and particularly interferometric mirrors, is among the most comprehensive diffuse optics methods to date. We can get, in addition to time-resolved intensity, we can get time-resolved autocorrelations, which gives us new dimensions, new ways of quantifying blood flow dynamics. And we show differences between brain and scalp that can inform, we think, our interpretation of conventional techniques. We can also make images. Okay, big question is, does interferometry help diffuse optics? And so I think here that these type of interferometric measurements for blood flow have a great potential to improve the brain sensitivity, which is essentially achieved by enabling a larger source detector separation for lower cost. And I think this will help improve blood flow index monitoring in general. It remains unclear whether this technology can compete with high throughput continuous wave mirrors for functional studies and brain-computer interfaces, although the initial results do seem promising that blood flow index gives us better measurements of activation than brain absorption. And in general, this interferometric method is a very useful gold standard, I think, to help our understanding of how superficial tissue anatomy and physiology can affect what we can measure from the brain, and can help inform the design of better diffuse optics methods that can be more specific to the brain. Okay, so with that, I'd like to thank my research team, in particular Dr. Wenjun Zhou and Oybek Kulikov, who did a lot of the work for the interferometric techniques, and my funding sources. And again, it's a pleasure to be here. Thank you very much.